Hello everyone, welcome to the first video for this week. So in this week, we're going to be studying how the derivative, the first derivative and the second derivative can be used to effectively kind of draw a rough sketch of the graph and to identify important points in the function, like points where the function is somehow the largest value amongst all points around it, and points where this function is the smallest value around amongst all the points around it. And these are called respectively like relative max and relative min, or if you want, relative maxima, relative minima. And these are very important applications when you want to optimize, say, your profits of producing something, or you want to figure out the least amount of quantity used to make a certain box or some kind of material or something like that. So this problem of identifying where functions are the largest and the smallest and understanding the shape of functions is really important in different applications. We won't get to the applications, unfortunately, until after the test. But this is a very fun topic because you really get to see kind of how the derivative can be used to say very concrete and kind of cool things about functions. And it's not, in my opinion, as challenging as the topic we did last week, where we have to do these approximations of functions using the tangent line and like all these physics problems, which can be, you know, somewhat more physicsy, is how we say, than mathy. So a little bit off the beaten path as far as understanding the overall concepts. Let me share some screens. I just want to mention a bit how this is going to go. Okay, so here's the yellow pad that hopefully you've come to know and love at this point. But I also will be kind of using, so I'm going to be roughly going from, takes a minute to get back on track here, slow motion. I'm going to also be using a little bit going off of these notes, but I'll use these notes for the graphs. I put them on Canvas. I don't like this fill in the blank thing so much, but you can fill them in if you want. I do want to expand upon it a bit, so that's why I'm going to use the yellow pad. But I'll come back to kind of use these graphs as example because they're a little hard to reproduce. They're kind of annoying to reproduce on the yellow pad, but we will be able to use the yellow pad for a lot of stuff. Okay, so that's enough BS for that. Let's get back to the yellow pad. Let's take a minute here. All right. And the yellow pad, as you know, does not have this terrible delay that the other application does. So I want to just, I mean, we've talked about this before, but this might have been way back at the beginning of the semester. So in decreasing functions. So, and again, you can follow and fill in the blanks if you want, or you can just make your own notes from the yellow pad. Whatever you want to do is fine with me. Whatever works for you. A function f of x is said to be decreasing. Sorry, I'll just do increasing first. If the graph of f rises as we move along from left to right, or in the positive x direction. Okay, so let me just draw kind of a picture of what that might look like. There's different ways you can do this, as we'll see in a moment. So here's one possibility, right? The graph is rising up the y-axis as you move along the graph from left to right. So as you move in the positive x direction, if you're on this graph, right, you're going to be climbing a pretty steep hill. And I mean, what this is saying is that, I mean, where the word increasing comes from is the following. So a more precise way of saying this is, i.e., the y values of the function f increase as the x values increase. So as you kind of get larger, keep getting larger in the x direction, the y values are also getting larger and the graph is rising. So that's increasing. Decreasing, you can imagine, would be the opposite. The graph is falling as you move from left to right, that the y values are falling or decreasing as the x values increase. So let me say that. So decreasing. F at x is decreasing if the graph of f at x falls as we move from left to right. Along the graph. So picture, and this is another reason why I wanted to use the yellow pad rather than the PDF, because I can draw a picture and you can kind of get a better sense maybe what's going on. So something that's decreasing might look like this, right? So as we're moving along the positive x direction, if you're on the graph, if you're a fellow on, if you can imagine yourself walking along the graph as you move in the positive x direction, you're going to be going downhill, right? So if this guy had some skis on, you know, you're going to be going down the hill pretty quickly. And another way of saying this more precisely is that, i.e., the values of f at x of y equals f at x decrease as x increases. Okay, so that's increasing and decreasing. Now, it's nice to have a graph, right? To kind of see things and, you know, just visualize it. But in many cases, what the point of calculus is, you know, not to start with a graph, and you can do that in pre-calc, but it's to start with a function formula, an algebraic formula, use calculus to determine which situation here you are in, right? So suppose you just start off with a formula like f at x equals x squared. How do I figure out, pretend you don't know the graph, how do I just figure out from that formula, where's the function increasing, where's the function decreasing? And well, luckily we understand derivatives now and tangent lines, so our knowledge of derivatives can be used to answer this question. So here's the main problem, well, a problem we want to kind of deal with this week is the following. Suppose we are, you know, just given a formula y equals f at x and not its graph. So let me just see which one are we going to do by the end of the week. Now, for example, say we're given the formula like f at x equals minus x cubed plus 3x squared plus 9x plus 1. Okay, this is one that if you look at it, this is one that formula that we will see at the end of the notes later on, in page 4 of the notes, and we'll be able to analyze this function quite nicely. But so, you know, if I just take a look at this formula, even with my experience from just looking at this formula, I don't know what the graph of this thing looks like. Okay, so I can't answer, like I can't just sketch it and say, oh, look, here's functions increasing, here function is decreasing. You know, I can't produce the graph. So we need to use calculus to get from this formula to some information that will allow us to produce the graph. Okay, so looking at this formula, how do we tell without the graph of the function where f is increasing or decreasing? And the answer, in some sense, is in the derivative. answer, we can use the derivative, the first derivative, f prime at x. So here's a little fact. Here's a little fact. So if fx is increasing, then the slopes of the tangent lines to f are positive. So if your graph is rising, right, as you move from left to right, then any tangent line is going to have positive slope. So the derivative will be positive there. So f prime at x is positive. And let's just go back and take a look at our little sketch above and see that that coincides with what our intuition is. So here we are, here's the guy. So here's your guy going for a hike up this hill. Maybe he has a little walking stick, all right? And you take a tangent line here, right? You see that has positive slope. So, and it's also positive here. I mean, maybe not as at the bottom of the mountain, maybe it's a little gentler slope, but it's still positive. And as you get closer to the peak, I guess it gets steeper and steeper. Okay, but anyways, anywhere along this graph, we see positive slopes of the tangent line. So let me put this in a nice color. Now, on the other hand, where we are here, go back up to the skier here, Winter Olympian. And given the weather this week, that's probably not a bad analogy. So if we draw tangent lines to this graph, right, this graph where the graph where the function is decreasing, right? If I can draw a decent tangent line, it's harder for me to do it when it's decreasing because you have to move the pen down. But there we go, it's not so bad. So for a decreasing function, we see the slopes of the tangent lines are negative, right? So in this case, the function is decreasing, we expect the derivative to be negative. So then second fact, so fact 2, if f at x is decreasing, so let me write this. Let's give you some room here. To f are decreasing, or negative, sorry. So the derivative, which is measuring the slopes of the tangent line, is negative. For decreasing f. Okay, so we can use calculus to start from a formula and begin to understand something about where a function is increasing and decreasing. But there's much more to the shape of a function than just where it's increasing and decreasing. So there are other things that, before I do an example of where you find something increasing and decreasing, I want to introduce a few more ideas that we'll use in conjunction with these ideas of increasing and decreasing to say a lot more about the function. So let's move on to that. So maybe do the next page. Let's click here. Okay, so let me go back to this kind of hiking analogy that I was talking about. So you say you have, I'll make the, I guess it's more realistic if you're hiking that you do something like this, right? And you come to the peak and you go back down to the ground, say. So you have a function that looks something like this. And as you move along here, so we'll call this point A, as you move along the X direction towards A, your little hiker keeps climbing the peak. And eventually, after a long day or a long morning or something, he or she gets to the top of the peak, right? And then starts descending, right? After having some lunch, taking some photos, what have you, they start coming down the mountain. Okay, right? So my stick hiker got taller as he or she descended. Well, okay, just suspend belief there for a moment. But this point A, where you come to the top of the peak, right? That's a very important point for the function, because it's a point where it's the largest value, the largest height of the function in the area in which you're looking at. And like I was saying at the beginning of the video, when you want to talk about maximizing profits or maximizing customers or something like this, you want to maximize a quantity that's good for your business or good for an application, right? You want to figure out what parameters do I need to get the function to be large as possible as I can, given my circumstances, given the area in which I'm working. And that point is called a relative maximum. And so we want to be able to identify these peaks without having a graph of a function. So let me so maybe this is stick figures are a bit of a distraction, so I can get rid of them, but I never did very well in art classes, you can imagine. I tried hard though. Okay, so let me say this. So a point in which the function point A, we can say, in which the function f of x takes on the largest value out of all of the points around it. This is a little imprecise, so I'll put this in quotes, is called a relative maximum. And again, finding relative maxima are very important in applications. So we'll get to those in the next few weeks, but we need to kind of, do the theory a bit before we can dive into the applications and get the payoff. Oh, relative, not reflexive, sorry. Relative, that was relative maxima. Those, we need to do that until we can get the payoff, do the theory until we get the payoff and find, how we can use it in our applications. So let me just highlight that. So the largest value. So this point here, drilling down into the mountain. So in this picture, AF at A is a relative maximum. Okay, so we also have a notion, as you might not be surprised, we also have a notion of a relative minimum, right? So now we got to go back to our friend the skier. So you come down, you're skiing, that's pretty sharp. Eventually you hit the bottom and then maybe you have to go back up. So here's our skier. Zoom, zoom, zoom. Get to the bottom, and then you have to work your way back up, the next hill, I mean, this is more like cross-country skiing. Okay. Again, the skier got taller after they passed the minimum, but okay. So this point A, the bottom of this valley, right? This is the point where the function is the smallest value amongst all the values around it, right? The bottom of the valley is the smallest height amongst all the values around it. That point is called a relative minimum. It's the minimum point in relation to points around it. Okay, so we can say that. The point x equals a in this picture, where the value of fx is the smallest compared to all the other values of f at x around it, is called, I'm going to put around it in quotes again, is called a relative minimum of the function f at x. So let me erase my beautiful skier and be a little more serious. Just a little bit more. AF at A. So here at this point, AF at A is a relative minimum. Okay, so now I should, unfortunately, there's this section, the one drawback of this section is it has a lot of terminology, but the terminology is kind of intuitive, I think. So a point that is a relative maximum or a relative minimum is called a relative or local extremum of the function. So extremum just being a point where like a value is extreme in the area around it, either extreme big or extreme small. And extreme doesn't mean like huge or super tiny. It just means larger relative to the values around it. So like the kind of, this is actually the literal meaning of extreme rather than the colloquial one. But okay, so another definition, another term, if the point A f at A is either a relative max or min, so it can be, or, you know, so one or the other, then we say A f at A is a relative or local, some people call this local, extremum of the function f at x. Okay, so I should just make some remarks before we do some examples. We should make some remarks about what can happen with these points, and then maybe just talk about how the calculus of this works in a little bit. And I think we're going to be, mostly the first video is going to be building up definitions and some new ideas. And then the second video, we're going to be doing more kind of nitty gritty calculus computations from function formulae. So that's going to wait probably to the second video for this week. So some remarks. A function, so the first remark, I'll clean that up a bit. A function f at x may have several relative extrema. So it doesn't have to have just one relative max or one relative min. It can have many. Some of them can be the same value. And some of them may even be the same value. Although we won't see a lot of that in this class probably, but you should be aware that can happen. This kind of phenomenon where they tend to have the same value happens more in trig, which I guess we don't really do. But just so you're aware of this type of thing, you can have like a function that's a wave like this. And it just keeps going on waving. Waves and waves and waves. Right. So in this case, I mean, here you have a relative maximum. Here you have a relative maximum. It's kind of coming up to one here, but let's go off the page. Here you have a relative, oops, oh. Sometimes with this Apple Pencil, it goes into the eraser mode without me knowing. So if I just touch it in a certain way, it will kind of start erasing. Okay, there we go. Let's clean that up a bit. It's really annoying. There we go. Okay. So like I was saying, with this kind of wave-like function, you have relative, now it looks like it's moved a bit, but you have a relative maximum here and you have another one here. I should just use the cursor, right? But you also have relative minimum here and relative minimum there. And these are relative minima that have the same values. And these are relative maxima that have the same values. So that can happen. Like you can have a mountain range with peaks of the same height, basically, is what it's saying, and valleys of the same depth. Like I said, I don't think we'll see a lot of this in this class. This tends to happen with trig functions. What I've drawn is a trig function, but it's good to be aware that does happen. The second thing to notice, to be aware of, is the following thing, which is not explained very well at all in the PDF, in the white notes, the white paper. Okay, so let me say the following. So if f at x is defined on a closed interval, so it's defined for some points a and b, right? For some x values between a and b. So it's not like going on for infinity like the example I drew above. Then the relative max or min value of the function may not actually be the maximum or minimum value of the function on that interval. Of f at x on the interval. The closed interval a, b. So this is usually called, I should say this is usually called the absolute maximum or absolute minimum. So what I mean, okay, so what do I mean by this? So I mean, if you have a function that's on a closed interval, and the function is continuous, which almost everything we'll ever look at will be, then there are points where, like on the interval, where the function takes on its largest possible value and points where it takes on its smallest possible value. Those are called absolute maximum or absolute minimum points. They may not occur at the relative maximum or relative minimum. This is a very subtle point, and it's very annoying, but it's something that you need to be aware of for the homework, and it was not explained very well in the notes. So let me just give you an example of what the kind of thing I'm talking about in pictures, so you believe that there's something going on here.
Okay, so it may not be the absolute maximum or absolute minimum value of the function on the interval, which is the largest value of the function on the interval AB, and smallest value of the function respectively on the interval HV, AB. Okay, so let me draw a picture. So actually, and I don't need to make it this large, but we can just do this something like this. So say you're looking at a function from like 1 to 3. It might start out somewhere around here, goes up to a maximum, relative maximum, and it comes back down to 3, to 0, sorry, to 0, to the point 30. Okay, so in this case, the maximum value, the absolute maximum value of the function happens to be at a relative maximum, right? But the minimum value here, so this is 30, is not at a relative extremum. It's at the endpoint of the interval, right? So in this case, the absolute max occurs at a relative max, AF at A, whatever that value happens to be. But the smallest value, the minimum value, occurs at the endpoint. Of f equals 0 occurs at the endpoint of the interval of the interval I said at the endpoint 30 of the interval -1, 3. Okay, so, but also it can also be the case. So you have something like this. We could also have a situation of like the following. So you have a max, but then the function keeps going up. So say this is 0 to 5 or something. So here you have a relative maximum. Maybe this is the point 2. But you have a relative maximum, but the actual maximum occurs at the endpoint. So for this function, we have a relative max at x equals 2, but the absolute maximum occurs at the endpoint 5, x equals 5. So you can have a relative extremum of one sort, but the maximum, the absolute maximum on the interval, the largest value on the interval, can still happen at the endpoint. And there are several situations about like this. It's not to say that it has to happen at the endpoint, I mean, I'll do one more situation, but then you can kind of dream up others. There's several, and I don't want to spend too much time on this, but you could have the absolute max min occurring at relative extrema inside the interval. For example, you could have something like that. So -1, say, to 4, right? So this is your relative max and absolute max. And this is your, over here, maybe we use a different color for this guy, blue. And this is your relative and absolute min. Okay, so if you're on, then there are other situations like this as well. So basically, the summary is the following, that if you have a function on a closed interval, then the absolute max or min of that function can happen at the endpoints of the interval or at relative max or relative min inside the interval. So that's what you have to look at when you're trying to find max and min of a function on the interval. Okay, so summary, and these are these examples are just to show you that that's any one of these situations can happen. That's what you need to check. So the absolute max or min of f at x on a closed interval a, b. So remember that closed interval a, b, remember that equals the set of x such that x is greater than or equal to a and x is less than or equal to b, right? May occur at relative extrema inside the interval, or they may occur at the endpoints. Okay, so when looking for these max and min, I should say it this way. We're looking for the largest and smallest values of f on the interval AB. Need to check local extrema and the endpoints. People often forget to check the endpoints. It's really important, but we'll get to that. Okay, so remember this fancy term, absolute max or absolute min on this interval is just the largest and smallest values of the function on the interval, respectively. Okay, that's all this term absolute, that's why it's called absolute. It's the largest but maximum, the largest value, or in the case of the absolute min, the smallest value of f on the interval. Okay, and we should do some examples of this. So when we're looking for them, we need to look at the local extrema and we need to look at the endpoints, because in these examples here, for example, the absolute max is at an endpoint. And in this example, first one we thought about, the absolute min was at an endpoint. But the absolute max happens to be at the extrema. And in this case, the absolute min is actually also at an endpoint. Okay, so those are the kind of things you need to be aware of. And I feel like 15 minutes explaining something that was called a note at the end of the one sentence of the PDF paper. So I'm going to pause it for a second so I can switch over to do some examples. Okay, so we're back, and I'm back on the notes, the PDF notes, so I don't have to draw this graph, reproduce this graph for you. So it's a little shaky there. Sorry about that. So this app has a lot of trouble responding, so we'll see how well this works. Now, I want us to this example, kind of talk a little bit about identifying where the function is increasing or decreasing, label any relative max or min, and I also want us to find the absolute max and min, like we've been talking about earlier. So for the increasing part, this isn't too bad. So it's also frozen again. So let me pause it again and see if we can fix it. Okay, so I'm having some issues with being able to write on this PDF, but this is a fairly qualitative set of questions, so I can talk through it. But the writing is delayed, as you can see, by almost 10 or 15 seconds. So we'll just talk through this question. Identify where the following function is increasing or decreasing, and let's label any relative max or min and the absolute min and max as well. So I added that part because we just spent 15 minutes talking about it. Okay, so where's the function increasing? The function is increasing, right? Where if you were kind of hiking along this trail, you'd be climbing, right, the mountain. Or another way of putting it, more precisely, the slopes of the tangent lines are positive, or the derivative is positive. So if we look, where do we have increasing? So this looks like we'd be climbing between 1 and the top of the peak at 2, right? And then you go down to the valley, and after the valley you'd be climbing from -2 to 2, and then you would go down to the valley, and at x equals 6, and then you would start to climb again. So again, function is increasing from -2 to 2, and then from 1 off to, I think these marks are about each 1/4, or they're each 1/2. So it looks like the endpoint is around 7. Where is it decreasing? So that's where you're going down the slope, and you'd be going down, and where the tangent line slopes are negative, or the derivative is negative. That would be from the leftmost endpoint, which is about at -3, to -2, and then after the peak, from x equals 2 to x equals 6, you have negative tangent slopes, or you have a negative derivative. Now, where are the absolute relative, any relative max or min? So we have a relative max, or the peak, I keep talking about it, at the point 2, 3. That's the largest point of all points surrounding it. So that's the relative max.
And you can kind of see from the picture that is also the absolute maximum. It's the largest value of the function on the interval we're looking at, which is like roughly -3 to 7. And the relative min, we have 2 relative min. They are actually the same height or the same y value, like I was saying can happen. And these 2 valleys of the same height or the same depth, if you like, occur at the points of -2, 1 and the points 6, 1. They are also the absolute minimum here. They are the lowest points of the function on this interval. So you have 2 places where you have reached the absolute minimum, and they happen to be at these relative minima. The endpoints are neither absolute max nor absolute min in this situation. So in the next question, you can just we can just talk about this quite easily. It's again now we're like what I was talking about earlier was translating the graph into calculus language, right? Increasing means positive first derivative, and decreasing means negative first derivative. So now we want to kind of go from that language, the derivative calculus language, to make sure we to the graph language to make sure we can understand from the derivative the right graph. So in this question, you want to identify which of the following graphs has a positive first derivative for all the x we're looking at. So positive first derivative means that it's all the slopes of tangent lines have to be positive. The function has to be positive for all x that we're looking at. So if you look at this, the first example, the function is actually increasing for all x, right? It's increasing less and less as you move along the x-axis in the positive direction. But in that case, all the slopes to all tangents there are positive, and we have positive first derivative. But for the next one, the parabola, you see the parabola, this is interesting. Parabola has a minimum, a relative minimum at 0. And so the function decreases until you get to 0, and then it starts to increase after you get out of the valley. So that you have a negative derivative going into the minimum, and then you have a positive derivative after the minimum. So the parabola does not have positive derivative everywhere. It decreases until the min and then increases. So that's out. The third graph is this graph I actually drew to illustrate a decreasing function. So for the third graph, the slopes of the tangents are all negative. The first derivative is all negative. So that's out. And the last one is just a line. And it's a line of positive slope. So actually for this last example, the derivative will be constant positive value for all x. So it's definitely has a positive first derivative. It's just a line of positive slope. That's the easiest thing we could hope for. So these last couple examples, I think, illustrate some interesting phenomenon that we're going to investigate in the videos in the next video. So let me just kind of foreshadow that for a moment. I can get off of this terrible app and go back to my nice app. So some observations going forward. Okay, so what do we have going forward? So we saw this is also very slow. Let's give it a second. Okay, so we saw in the last example that for the parabola, y equals x squared. So that second graph at the bottom of page 1,
right? That here you had this relative min, this value, right? And the function to the left of the relative min was decreasing, and to the right of the relative min had positive derivative. So that actually tells us how to find relative min using calculus, because I haven't even mentioned that yet. So we've just been talking qualitatively about these points, how they relate to max, the absolute max and min, how to find them graphically, right? So, but remember I was saying at the beginning, the whole point of this week in some sense is to forget about the graphs once we qualitatively understand what these terms mean, or remember what they mean from pre-calc, and use calculus to be able to get that information from algebra, from knowing the function formula, or from the mathematical model you have for some application, which we'll get to after the exam. So, but these examples we're thinking about give us hints as to what we should be looking for in calculus terms to figure out how to apply calculus to find these points, these relative min and relative max. And what we see with the parabola is when you're coming into the bottom, the valley, right? You're decreasing until the valley, so your derivative is negative until the valley. And then after the valley, you start hiking back up the mountain range, the derivative becomes positive. The function starts to increase. So here's the fact. If the point x equals a is a relative minimum of the function, sorry, y equals f at x, then the derivative switches from negative to positive as we move across the minimum. More precisely, f prime at x is less than 0 for x less than a and near a. So it's just near the point, just slightly to the left of the point. The derivative is decreasing. So the derivative is negative, the function is decreasing. And when we go over the point, it becomes positive. And f prime at x is positive for x greater than a and near a and x close to a. Now for the parabola, it's negative all the way to the left of 0, right? The derivative is negative for all negative x, and it's positive for all positive x. But that doesn't have to happen in general. You could have a situation like this, where here's your a, and what you see is that just close to a, right to the left of a, the derivative is negative, and just close to a, to the right of a, the derivative is positive. But then things can change as you get far away from a, right? So it just has to happen to get a valley. You just have to happen in a snapshot. You just have to take a snapshot of what's happening around the point A, right? And in that snapshot, it's negative to the left, the derivative is negative to the left, it's positive to the right. And for a max, the opposite situation happens. The opposite happens. So what does that mean? So if x equals a is a local max or relative max, then f prime at x is positive for x less than a and close to a. And f prime at x is negative for x greater than a and close to a. So in other words, as you go across a relative max, the functions, or you move across a relative max or a peak, the function switches from increasing to decreasing as you move across the max. So i.e., at a relative max, peak, the function switches, the function goes from increasing to decreasing as you move from left to right. And we can see that in the picture above. So if we instead look at the point, say I'll keep it a different name. If we look at this point, I'll call this point B, right? That's a relative max. Here you have f prime at 0, sorry, f prime greater than 0, just to the left of B, and you have f prime less than 0 to the right of B. It switches in this snapshot. We take a snapshot, right? It switches, the function switches going from increasing to decreasing as you move across the maximum. And the same thing happens at this other relative max here. You have switch from a positive derivative to negative first derivative as you move across the maximum. Okay, so looking at these pictures, analyzing these pictures tells us what we expect the calculus to say about where to which points are relative max and relative min. A relative min, the derivative switches from negative to positive. The function goes from decreasing to increasing as you pass across the min. For a relative max, it's the opposite. The function switches from going increasing to decreasing, from positive first derivative to negative first derivative as you move across the max. So this gives us a hint on really how to find these with calculus. What we'll see is to find the relative max and relative min. If the derivative is switching sign at the max and min, that must mean at the max and min, the derivative is exactly 0. Right? So if you go from positive to negative, or negative to positive, as you go across these points, at the point itself, the derivative will be exactly 0. And you can see that, you get flat tangent lines. So we now know, find the points, we're going to develop a procedure. Find the points where the derivative is 0, and then see if it switches, how the derivative switches sign around those points. Does it go from positive to negative, or does it go to from negative to positive? And that's what I'll talk more about in the next video. So thank you for tuning in. That's enough for now.